So that brings us to this key subject. How does this animal move around, look at this background, and so quickly achieve adaptive coloration? So experimentally, we're lucky because the cuttlefish or an octopus is an animal whose primary defense is camouflage. So they are just genetically driven to camouflage no matter what background you give them. It's an astounding feature that we can exploit in the laboratory. And the concept that I'm really going to posit to you right now is that if there are only 3 basic pattern types, then to achieve this fast change occurring in less than a second, they can't have a brain the size of this room to analyze all that information. We think that they're ignoring a lot of the visual information and looking just at 1 or 2 key attributes of the background to turn each of the pattern types on. That could account for the speed, so consider it a working hypothesis. Okay, so the animal's eye is rather unusual. When you look at this eye, if you look in cross-section, it looks very much like the cross-section of my eye or your eye, but it's actually arranged very differently. But I will point out in the brain of this animal, these kidney-shaped things on the brain are all optic lobe, and the center part here are 20 or 30 other lobes of the brain. This is clearly a visual animal, but we don't know exactly what those lobes are doing. So we have a large complex eye, huge optic lobes, they have very keen visual acuity. Curiously, they can see polarized light. We cannot see polarized light, not that many animals can. They can see very well at night. I'll show you some data on that. Yet, curiously, they seem incapable of color vision, which has some ramifications for the idea of colorblind camouflage, because their predators do see color for the most part. So how do they get the color right? All right, here's the experimental design. So you see in the top here, we've got environmental information which we present to the eye of the cuttlefish. And then, because it's genetically driven to display some kind of pattern, we've got our 3 pattern types right here. And bear with me, let's see if it really is just 3 pattern types. And the idea is we put a cuttlefish in a uniform background like this, we give it a non-uniform background like that, and we give it a non-uniform background of different scale and different contrast, and the animal is now morphed from uniform to mottled to disruptive. Now, what are the cues there? The cues here are black and white, small scale, moderate contrast. The cues here change by spatial scale and by contrast. What are they really paying attention to? Well, first let me show you a dynamic example of the change on a real substrate rather than the strange ones I just showed you. So here's a cuttlefish on a sandy bottom showing a nice uniform background, and somewhat cruelly we pull the rug out from under it and it sees this non-uniform background and immediately begins to change its pattern, and it settles, a little upset because we moved it, but you can see it goes into this mottled pattern. It would get rid of that little white square if we gave it just a moment, because that's a disruptive mark. But instead, our special talented 3-handed technician reins in white rocks from heaven. And look, the cuttlefish looks at the white rocks and specifically goes over and changes its pattern dramatically into a disruptive pattern. So I think you can understand if the animal had stayed here, the camouflage would have been very good. Would have been mottled on a mottled background, and that was effective. But there seems to be a priority rule here. When the white rocks showed up, the animal went into disruptive coloration. 80% of the visual field would tell the animal to go mottled, but instead it took the 20% of the information and went disruptive. So what's going on here? The idea, again, is that we think there are some visual cues here that are simple, and we're going to try and sort those out experimentally.